Tuesday, we talked about the midpoint rule, right? Midpoint rule, and we're going to study two more rules, and then we'll talk about a very general type of tool for integration. It is, in terms of the degree of exactness that we mentioned, is the highest possible, right? It's magic. So we'll do two more regular ones and then move on to that. The midpoint rule plus the next two, right, would fall into the same category. So let me try to outline that for you. So again, the goal is that we need to evaluate some integral, right? Some integral. We need to come up with an approximate value of an integral of function f, right, between a and b. That's the goal. And the idea behind the midpoint rule is that you come up with a constant. We take the midpoint, we take the function value at that point, remember, right? And we, by evaluating the area of the rectangle, we actually, what are we doing actually is integrating the constant function. I hope you see that. If you're integrating a constant function, you're just calculating the area of the rectangle. All right? If I integrate function 2, all right, from 0 to 2, obviously that's just 4. Right? That's 0, the integral of a constant. Okay? So in that sense, we're actually approximating f of x by f0 of x, a degree 0 polynomial. Okay, if we approximate f of x by f of 0x, this would lead to the what we just did Tuesday, midpoint rule. Does that make sense? We approximate it by the interpolating polynomial, right? The point being the midpoint. The interpolating polynomial, remember the fn. Of course, as the moment we interpret this way, we can extend it to degree 1, degree 2, and so forth, right? We don't have to do degree 0. That's exactly the idea that I want you to get here, right? To go from midpoint to the other two rules. If you understand that rationale, the three are, pretty much the same. Okay? Does that make sense? Hope. So in general, if you will approximate f of x by fn of x, a degree n polynomial, interpolating fx at n plus 1 points, right? x0, x1, xn. Okay, degree 0 is just 1 point, x0, which is midpoint. Okay. So this of course we can do it. We already have tools, right? We know f of x, fn of x, okay, is this summation, right? I from 0 to n of my function value at xi times my Lix. Lix being the characteristic polynomial. Right? Okay? So what does this mean? Once you have f of x, the numerical integration n f, which means we're going to use the polynomial degree n to approximate f, and we don't want to integrate f for many reasons, including we cannot do it, or f is simply not available. Okay, even if it's available analytically, it doesn't mean you can integrate it, right? So we're going to use this guy which is integral from a to b, not f, but this approximation of f, right? Fn. That's exactly what we started doing. And which of them is equal to because we have a form for Fn, right? So we are integrating Fn, which is summation from i is from 0 to n, our fxi lix dx. Okay, dx. All right, I just plug in f sub n x. Questions? So, a little bit of algebra. We have summation, we have integration. A finite sum here. We can switch the order. Integrating a sum is equal to integral of a sum is equal to the sum of the integrals. All right, it's basic calculus. So we move on to, okay, this is summation I from 0 to n of fxi. That's a constant. It has nothing to do with x. It's f evaluated at some points. So I can pull that outside of the integral. I'm going to integrate from a to b of my lix dx. Right, lix dx. Okay, lx dx. All right. So this form is revealing. Is if we call this alpha I, what do we have? We have a summation I is from 0 to n alpha I f xi. The alpha is the integral of the characteristic polynomials. It has nothing to do with f. The same for all f. That's the point. All right, this alpha I is the same for any f, as long as, of course, the points are fixed. As long as the interpolating points are the same. All right. Because those Li of x are determined. Remember that what is Li of sub x? The alpha I is simply an integral, all right, of this product. Okay, j is from 0 to n. J is not equal to I of the x minus xj divided by xi minus xj, right? Dx. That has nothing to do with f. There's no f in it. Okay, not in it. So what are we doing here? Again, you need to look into the essence, right? The essence is that we don't know how to compute the integral, so we do it numerically, right? It's pretty much always the case. You need to do things numerically. The numerical value of the integral, right? This can be approximated by a sum I from 0 to n alpha I f xi, which is your integrated function is the same as you evaluating the function at a bunch of points and multiply with some weights alpha I. So we turn integration into evaluation. That's the key. Which is, if you're smart enough, you need to know where to evaluate. As long as I can figure out where to evaluate, I evaluate at the good points. We're going to talk later. We have points that are better than what we do now. The midpoint maybe is the next two endpoints, right? But you need to know where to evaluate. When you need to integrate, you need to evaluate the function at some points. More than that, okay, you need to know what weight to multiply. If you know both, you're done. All right. As long as we know the xi alpha I, we're done. That's all we need. If you give me xi alpha I, you tell me that's a rule. Now I'm going to evaluate the function at xi, right? And we'll multiply that value by alpha I, and sum them up. I get my integral. That's essence here. That's essence here. Okay? So here, that's called the quadrature. This is called quadrature. Quadrature rule. You give me points, you give me weights. So points and weights. Well, I evaluate my function at those points and multiply with the weights. I add them up. Example, I mean, again, that's essentially what we did already. The midpoint rule is the midpoint. Rule is what we did on Tuesday. The ni0, right, of f is simply the function value, right? The function value f at c, which is a plus b over 2 times b minus a. B minus a. Okay? Yes. So the next one is a new rule, is a trapezoidal rule, so-called trapezoidal rule. And as we were saying, we now use F1, right? We now use F1. And we're going to end up with Ni sub 1, the degree 1 in approximation, which... So when you need to integrate a function from a and b, right, a and b, and if we're talking about, okay, I have 2 points a, b, all right, I'm going to generate a degree 1 polynomial, which is, of course, just straight line, right? So this red line, all right, and I'm going to evaluate this. The trapezoid, right? This area of the trapezoid, which we can simply write it down. We certainly don't need to do this. Is b minus a times a half fa plus fb, right? Fa plus fb. All right. So you can if you have a polynomial, if you have a quadratic, what this is doing is evaluating this guy, right? Which is that. So we can already see this is not going to be exact for polynomial of degree 2. Right, which is expected. That's an intuitive graph. So this says that the degree of exactness of this rule is what? Degree of exactness is still 1, like the midpoint rule, right? Is 1. It's 1. Okay, it's 1. And let's evaluate the error, right? With the midpoint, we use E, should have E sub 0, F, degree 0, is degree 1, D1. And we have from A to B of F of X minus, it is interpolant, degree 1 interpolant, dx, right? dx. Remember we had the interpolation error theorem, right? We did prove that. We know that f of x minus in f of x, right? This is equal to f n plus 1 at some c divided by n plus 1 factorial, right? Times omega n plus 1 x. That's what we showed when we talked about interpolation. And again, what I just said is that if you use degree n, you can recover degree n from this theorem. You know that again, right? If f is a degree n, degree n polynomial, you take its n plus 1's derivative, you're going to get 0. So the error is 0 by this theorem. The error is n plus 1's derivative be evaluated at some c, but the whole function is 0. So it's 0. So the error is 0 for polynomial degree n, which means if you are interpolating a polynomial of degree n by a polynomial degree n, you can recover it. That's what we just explained. So by using this, we know we can derive this numerical integration error. So we're going to get what n is 1, right? So we have f double prime at c divided by 2, right? That omega n is x minus all the nodes, right? So it's x minus a times x minus b dx, right? dx. Okay, and that's nothing but we can take out the f double prime c over 2, right? Over 2. We only need to integrate x minus a times x minus b. The first term is x squared, so we're going to get what? X cubed over 3 between a and b, and then we have ax, a plus bx, right? So minus ax minus bx, so it's minus a plus bx, which is a plus b x squared over 2 between a and b, right? Plus, finally, we have a times b times b minus a, right? That's integral. Okay, that's integral. And so we're going to get f double prime c over 2, right? We have 3 b cubed minus a cubed, right? We're going to have, let's do this, common denominator 2. Okay, with a, we have, what's that? A plus b times b squared minus a squared, right? Okay, evaluate x squared at b and a. And we have plus ab times b minus a. We have 2 below, so we have minus 2ab b minus a, right? Okay. All right. So what's this? This f double prime c over 2. We have 3 b cubed minus a cubed. All right. We can actually factor out the b minus a, right? If it's for those. So if we factor out b minus a, what do we get? Yeah, for the first term we have 3. The factor of b cubed minus a cubed, so it's b squared, yeah, plus ab plus a squared, right? And then we are going to get 2 b minus a factor out of b minus a, b squared minus a squared factor out of b minus a, you have b plus a, which is a squared plus 2ab plus b squared. And then we have a minus 2ab, right, from the factor of 2ab b minus a. Of course, we're going to cancel that. 2ab. Yeah. So we ended up having what? You'll see it's a very much similar to the midpoint rule final result. All right. So it's f double prime at c divided by 2 b minus a. Okay, b minus a. You have, what do you have? You have 6. All right, you have 6 common denominator, and you're going to get what? 2a squared plus 2ab plus 2b squared minus 3, right? 3 times 3a squared minus 3b squared. Right? What are we getting? So 2a squared minus 3a squared is a negative a squared. 2b squared minus 3b squared is negative b squared. And you can complete the square. It's a minus b squared. B minus a squared. The same thing. And then you have b minus a already. So it's a negative b minus a cubed divided by 6. Okay? You get that? If you recall, we concluded on Tuesday that the error for the midpoint rule, this guy is what? Is f double prime c over 24 b minus a cubed. Here, the trapezoidal rule, the error is negative f double prime c over 12, right? 2 times 6. Also b minus a cubed. Right? And again, this also shows that the degree of exactness is 1, right? It's 1 for the trapezoidal rule. Does this necessarily mean the error for the trapezoidal twice as large as midpoint? All right. So again, this does not mean the error for trapezoid is twice as much of the midpoint, right? Because c might be different. The next is you want to do this a composite trapezoidal rule, right? Composite trapezoidal rule, all right? And as we were doing for the midpoint rule, we have h, which is b minus a divided by n, right? Divided by n. Okay. So instead of you treating it as one interval, you do many intervals, many smaller intervals, right? So and so forth, and on each one you're going to use a trapezoid on each piece. Okay, that's the idea. That's the idea. You use a whole bunch of trapezoid. You do piece by piece, smaller intervals, and on each smaller one, you do a little trapezoid. All right. So this, if we write this as x0, x1 is an xn, right? Is an xn. So we're going to get the ni1 a composite, right? Well, let's use C to denote the composite F. This will be you do the same thing as we did above, all right? The trapezoid, which is x1, the first one is x1 minus x0 times, the average of f of x1, f of x0, and they all have size h. So you're going to get h times a half f x0 plus f of x1, right? Plus the next trapezoid is a half f x1 plus f of x2, and all the way to the end, you're going to get a half f xn minus 1 plus f xn. All right, xn. It's the area of trapezoid, right? Well, we did already from A to B. We now do that on the one smaller one, the base h. If we were to write a little differently, the x0, the first point, only appears once. Starting from x1, it appears twice, right? Because x1 is involved with the first interval, is also involved with the second interval. So x1 appears twice. Only the two endpoints appear once. Everybody else in the middle appear twice. So this can be written in a way that's more consistent with what we had above. So that is h is b minus a, right, over n. So if we factor out the 2n, right? For the evaluation, we're going to do f of x0, right, plus summation of f xi, and here I is from 1 to n minus 1. And you have 2 outside, plus f at xn. For the x1 appear twice, so 2f of x1, right? I replace my h by what by its value. Yes? For the error, we can, as we did for the midpoint, we just reuse what we did above. The composite form, the error is then you're going to have a summation on each piece. All right, I is from 1 to n. On each one, you have that guy from above, right? F negative f double prime at some c I over 12 of the b minus a is now is b minus a for that little trapezoid, which is b minus a over the n, right, cubed. Okay. And you multiply this, you multiply a smaller number, you add a smaller number n times. So that's like multiplying by n. So this can be treated as n times the negative sign f double prime at a single c divided by 12 times h, right? So that's h. Our new b minus a is h cubed. All right, and this multiply with h cubed, which is h cubed, and what we do is that this n times h is b minus a, so it's a negative b minus a f double prime of a c divided by 12 times h squared. All right, n with one h makes b minus a. That's the definition of h. Right, this means that n times h is b minus a, which is what we're using over there, right? Which is what we're using over there. H cubed is h squared times h. And this guy is what we used here. the next is we keep going the so-called Simpson's rule. So what about we use the degree 2, right? Degree 2. Ni2f. If we do this f2x dx, right? It interpolates f1 the function f of x at 3 points. The natural 3 points are how if you put 3 points on the interval a b, the 2 endpoints plus midpoint. It will be natural first choice. Those 3 points. A b and the a b plus a plus b over 2. If you do the calculation, basically you integrate what we did in the top of the framework, the characteristic polynomials, you're going to get the following, which again just some calculus, some algebra. I'm not going to do that. You're going to get b minus a. You're going to get b minus a, and then you're going to get 1 over 6 fa plus 4 over 6 f a plus b over 2 plus 1 over 6 fb. fb, right? And again, you just integrate the corresponding characteristic polynomials. You get those numbers. L0, L1, L2, right? If your calc 1 is shaky, that's something you should do later. Just integrate those functions. 3 quadratic polynomials, you're done. 3 points, you get 3 quadratic polynomials. Integrate them. All right. So that's a very useful formula. What that says is that well, for what we just talked about, the quadratic points, the quadratic rule, you turn integration into evaluation. You just need to know the nodes and the weights, right? What we talk about from the midpoint is that, hey, we can use the midpoint, which is a plus b over 2, and the weight is 1. 2, this is the midpoint. 2, we should use the 2 endpoints a, b, and then we should use the alpha I should be 1/2, 1/2, right? That's a trapezoid. Now to Simpsons, we mean is a plus b over 2, b, and then the weights. The tricky part is the weights is not 1/3, 1/3, 1/3. In particular, right? Because there's some mathematics going on in the background. If you integrate those guys, you don't get 1/3, 1/3, 1/3. If you actually go back and do it, integrate those 3 quadratic polynomials, right? And which you should do to appreciate this. You're going to get 1/6, 4 over 6, 1 over 6. Right, this is Simpsons. Okay, Simpsons. By similar analysis, and we can evaluate this E2f, right? This is just the integral from of the f of x minus the integral of f of the interpolating polynomial f2 x dx, right? You put in the error, and you simplify. In the end, you can either work this out or again read the book. The book has all the details. You're going to get, this is a more complicated, 1 over 90, I think it's b minus a over 2 to the 5th power times f to the 4th derivative of cos e. Of cos e. Right, of cos e. This means that again, we're not proving the details here. This means that the degree of exactness for Simpsons is what? 3, right? 3. The fourth derivative of a cubic polynomial is 0. So the error will be 0 for a cubic polynomial. Right? So if we include that above, maybe remove this below, and here is a rule. Here is the degree of exactness. That's 1, that's 1, that's 3. All right. So obviously within these 3, the best to use is just simple. So again, the cancellation helps, right? We get degree 3. Also, it only recovers degree 2. If we, for the composite rule, right? For the composite rule, the E2, if it's composite, right? Again, we're going to get a summation, all right? Summation I from 0, from 1 to n. Okay, you have this constant 1 minus 90 times 2 to the 5th power. All right, and you have this h, b minus a is now the h to the 5th, right, times f to the 4th derivative of cos e, right, of cos e I sub I, we have been using sub I, and this is the same as you have 1 over 90, 2 to the 5th power, you have n of them, now add some single cos e times h to the 5th, and use the same trick again. N times h is b minus a, so it's negative b minus a over 90 times 2 to the 5th of f to the 4th derivative of cos e times h to the 4th, by which we meant that again you have a little function and you are integrating on a larger interval, so you cut that into smaller intervals. Now the difference between this and the trapezoidal rule is that you need a middle point for each one. Right? Don't forget about that. You need a middle point. So I would need a middle point. I would need the original points of my intervals, and then I'm going to take a middle point, right? Midpoint. Okay, midpoint. Okay, and I'm going to number the points a little differently. Before we're using x1, x0, x1, right? Before, remember, we're just using x0, and the next point is x1, and then we need a point in the middle. So you can either accept x sub 1/2. Normally we don't do that. So I would call originally just x2, right? Our original x1 is now x2. Here we're going to get x1, and x3 is x4, so on and so forth. Right? So n intervals, the endpoint is x2n, and this guy is x2n minus 1. All right? It's just numbering, that's all. Okay? If you do that, right, if you number in that way, what we had above is for each piece, we have, what do we have? We have, you're going to get 1/6 here, right? 4/6 here, and then you're going to get 2/6 here, right? For the first piece. That's the weights you should put. The weights. No, just, sorry, 1, right? 1, 4, 1. That's what we had above. On the second piece, you're going to get another 1/6, and then 4/6, 1/6. Right? That's the weight you should put. And this guy would mean the same point. So you get 2 times 1/6, which is 2/6. Okay? That's going on everywhere for those originally points, though not the half points. And that's exactly why if you see a formula in the book, that will be like B so that will be B minus L/6. All right. The first point is just f of x0. X0 only appear once, right? It's there's no another 1/6. For the x2, so for x2, x4, x6, all the way to the last one here, the weight is 2/6. You have 1/6 outside, so it's 2, right? So plus 2 times summation of those f and x2i's. X2, x4, x6, so on and so forth. And here I is from 1 to n minus 1. Because you wouldn't include the last point, 2n. It's only up to 2n minus 2. For 2n minus 2, for the 2n minus 2, you get 1/6 here, 1/6 there. Right? And plus, for the middle points, for the x1, x3, those half points, the number is 4, right? So it's 4 times the summation of f of x2i minus 1. I is from 1. When I is 1, 2i minus 1 is 1. So that's x1, right? Until all the way here, the last one. The last half point is 4/6. So that point is 2n minus 1. So that's why this is the upper limit is n. When I is n is 2n minus 1. Plus finally, the final point, which is f. This is like the first point. This. Okay? Last weight is again 1/6. Summation of weights alpha I f at those point xi, right? I is from 0 to n, right? That's what we have done so far. When I 0, 1, 2, we obtained the midpoint. I'm going to write down this again, and then the trapezoid and the Simpsons, right? The same framework. You can keep going, of course. Degree 3, degree 4, and there's a name for this, right? If you the n points, if you put n, so it's n plus 1 points, right? N plus 1 points, n is equal to 0, 1, 2, you can keep going, 3. If this n plus 1 points is evenly distributed on the interval, right? On the interval, then you ended up with a rule, with a quadratic rule, right? What I talk about, the weights and the points, and this is a so-called Newton-Cotes quadrature rule. Quadrature simply means that, as we were talking, you turn integration into evaluation. That's quadrature. Doing quadrature means that you just evaluate at the points, and then multiply with the weights, add them up, you get the approximate integral. That means quadrature.